So in continuation, we will look into universal shift registers, okay, wherein uh, how this can be employed for various tasks. Okay, so we have seen that these registers can be either unidirectional or it can be multi-directional, right? Or I can say bidirectional. So I have spoken about the bidirectional capability of the register in the previous lecture. Okay, you can just refer to that on the website. And the unidirectional capability is moving the data from one end to another, right? So that is meant by unidirectional capability. When I say bidirectional, then the data is capable of moving from the right to the left or from the left to the right. So in this case, we'll be using an important parameter, right? We'll be using an important component. Can someone name what is that component? This is a very important logical component which we discussed about, enabling the feature of bidirectional capability. What was the most important parameter? Yes, can someone recall? It's the inverter, right? So inverter was giving us an option where we could totally send 0 to one line and 1 to the other line, right? Okay. So we have seen this configuration, serial in, serial out. Okay. So data comes bit by bit and data goes out bit by bit, right? So it can be either bit by bit entry or parallel exit. Okay. Or it can be parallel input and parallel exit or parallel output. Similarly, parallel in and serial out. So basically, we are having combinations of all um, the serial and parallel. So taking these two into consideration, okay, we are having all of these combinations that we can think of. Okay, fine. So when you say serial, then what's going to happen? Bits are going to come symbol by symbol, or I can say bit by bit. Data is going to be transferred bit by bit. But here, when I say parallel, simultaneous, right? Simultaneous feature comes into existence where a lot of data can enter and lot of data can exit. Right. So today we will just concentrate on universal shift register. Okay. And if any doubts, then yes, we can work out with the other things. Fine. So this is your universal shift register wherein we have used D flip-flop. The reason why we use D flip-flop is it has just one input, and our motive here is to move data or probably store data using flip-flops. So collection of flip-flops together is called a register, right? So based on the number of flip-flops, I can say that it's handling those many number of bits, isn't it? So here I have the first flip-flop, the second one, the third, and the fourth. So accordingly, I'll be getting my outputs A, B, C, D. So QA, QB, QC, and QD, right? Okay. So here we have a feature called mode control. Okay, S1 and S0 are your select lines. Now I think all of you are very much aware as to what is a mux. So mux will have inputs and it will have an output. Mux will have one output, but then it will have multiple input and it will also have select lines. So you can just concentrate on this uh, table here, okay, which is towards your right hand side, okay, just on this table. Yeah. wherein you can think of 0 0. Okay, when you give 0 0, then you have hold operation. Hold, when I say hold, it means that data is retained. Okay, there's no option that data moves from one point to another point. Okay? So that is hold. Next, when I say shift right, which means data moves from one point to another point. So data is moving from the left side to the right side. So data is starting from the left side and then it is moving towards the right side. So that is referred to as shift right. Next, the opposite way. Okay, shift left. So which means whatever data is available towards the right hand side will keep moving towards the left hand side. Okay, then at the last we have something called parallel load. Okay, so this is used for uh, you loading the data parallelly. So which means here we have left shift, okay, and then we have right shift, okay, then we have parallel input, we can retain the data. So all the operations are possible with universal shift register. Okay, now let us see as to how exactly this shift register functions. Okay, so I want all of you to concentrate. So let's say we have used 1 1. Okay, we are using 1 1 as our select line. Okay, so 1 1, which means parallel load. So when I say 1 1, so which means it is referring to 3, isn't it? So this is 0 1 2 3, right? 0 1 2 3. Okay, so which means I3 gets selected, right? Whatever is at I3, that comes across the output. I3 is getting selected. So whatever data that is here, IA will actually enter. IB also will enter to the second flip-flop. IC also will enter to the third flip-flop. ID to the fourth flip-flop. So when this enters, okay, uh, across the output, you would have the function. So which means I3 is actually here. I3 is there. So I3 is getting inside your flip-flop. I3 is getting inside your flip-flop. So once it gets into the flip-flop, the same thing will appear at QA. Okay. So because that data passes here, right? And the same data comes out as QA. Similarly, IB gets in. Okay. So this is the path, gets in, and then it comes across the output as QB. Similarly, IC giving us the output QC. Similarly, ID giving us the output QB, right? So this is how your parallel load operation is happening. So which means 1 1 is referring to parallel load. Now let us see when we have 0 0. Okay, so when we have 0 0, it should actually hold the data, right? It should hold the data, right? So 0 0 means it is referring to I naught, isn't it? It's referring to I naught. So I naught is connected to I1, right? And here you can see that the output that comes, okay, let's say I naught comes here, and the same data is here. Okay, so I naught comes here, okay, and the same data is actually here. Same data is there. Okay, so it's a loop that is happening. Okay, and similarly here, if you can see I naught, okay, let me use one I naught. Okay, so the same I naught is retained. Okay, so which means when I naught is selected, the same data is held. Okay, so similarly here also you can see the same data is held. Okay, there's no transfer or shifting operation, right? Any doubts here? You can please ask, right? So the same data is held. I naught comes here, comes to the output, to the input, output as QD. The same thing is connected, right? The same thing is connected here via this line, right? You can see this line here via this line, and again the same thing gets in, right? So the hold operation we are able to perform, and we saw the parallel load also, right? So next we will see how 0 1 shift right happens. So when I say 0 1, okay, it means uh, your shift right should happen. So for shift right, we will give input here, serial input we will give here. So it can be a binary data 10111 or 1000, something, some binary stream that you will be employing or you will be giving via this input here. Okay, so I1 comes here as the output. The input that is selected here, the same thing comes here across the output. Okay, and comes here as the output as QA. Okay, and if you can see here, right, I1, it is coming here, QA, right? So the same thing comes here. So which means it is getting shifted, isn't it? I1. Then I1 comes across the output, enters into the flip-flop, exits as QB. The same thing is, same line is connected here. Okay. So this is now shifting to the next mux and then gets into the flip-flop, comes out as QC, and then gets in to the next mux via I1. Then you have your function output getting inside the flip-flop and the final output. So you can see that there is a shift that's happening from one flip-flop to another flip-flop, right? Yes or no? So we have finished hold, shift right, parallel load. So now we will see how this shift left happens. Okay. So if I say shift left, then I2 should be selected, isn't it? I2 should be selected. So now we will see similarly like how you were giving for shift right, for shift left also you are giving data here from the right side. So I2 is getting selected because it is 1 0, right? So this comes out as the output. Okay, and this gets connected to I2, right? I2 gets here, gets into the third flip-flop, comes out, and then it gets in here, right? The same thing comes here to the second flip-flop and comes down, and then now it is entering into the first flip-flop. So I2 is selected, the output comes, and finally you will have your bit, which is QA. So from here it is shifting. Is that clear, all of you? So in this fashion, okay, we are able to perform hold, shift right, shift left, and parallel load operation. And hence, we have the name universal shift register. Universal shift register. So this is able to perform all the functionalities, right? All the functionalities which is actually mentioned here as per the truth table, right? So one more thing that you can see here is it is in the form of IC. Okay, you can get it as a standard package, and it's in the form of an IC. So you have clear and you have clock signals that are actually enabling each flip-flop. Okay, so you can see that the clock signal is connected, okay, from this line, and it keeps going to each flip-flop here. Okay, to each flip-flop it is connected, okay, in this fashion, right? And then if I want to clear my data, okay, whatever data that is inside the flip-flop, that can be done with the help of clear option. Okay, so all the data can be cleared, which means I can feed 0 to them. So once 0 is there, then none of the flip-flops will have any data. So I can start fresh, thinking of either holding the value or shifting the value to the left or right, or having the operation of parallel load. So if I have this universal shift register, I'll be able to do multiple operations. So of course, it seems a little complex, but then as you try and understand, okay, each step by step, each step, then it becomes easy for you to analyze. Okay, any doubts here? Any doubts?